Alrighty, welcome everyone to day 11 of Advent Code. As I mentioned in the previous day, today is not being done at midnight. It is actually 12 hours later. It's now past noon for me here at Eastern Time. We're just getting started, but yes, anyways, the following ones, so starting tonight, I'll be doing them back at midnight. But anyways, ignoring that, let's get back to the problem, and let's see what day 11 has in store for us. So, you enter a large cavern full of rare bioluminescent Dumbo octopuses. Is that what it is, plural? Anyways, they seem to not like the Christmas lights in your submarines. You turn them off for now. There are 100 octopus arranged neatly in a 10-by-10 grid. Each octopus gains energy over time and flashes brightly for a moment when the energy is full. Although your lights are off, maybe you could navigate the cave using the disturbing, or without disturbing the octopus, if you could predict when the flashing of the lights will happen. Each octopus has an energy level. Each submarine can remotely measure the energy levels of the octopus. Your inputs, for example. It's an example. Inputs. The energy level of each octopus is valued between 0 and 9. Here, the top left octopus is energy of 5. The bottom left is 6. You can model the energy levels of flashing lights in steps. During a single step, the following occurs. The first energy level increased by 1. Then any octopus with energy level greater than 9 flashes. It's supposed to be greater than 9 to flash. Okay. This increases the energy level of all adjacent octopus by 1, including octopus that are diagonally adjacent. If this causes an octopus to have an energy level greater than 9, it also flashes. This process continues as long as the octopus keep having their energy level increased by 9. An octopus can only flash at most once per step. Finally, an octopus that flashed during the step has its energy level set to 0, as used all the energy to flash. Adjacent flashes can also cause an octopus to flash on a step, even if it begins. Okay. So given the starting energy levels of the double octopus in your cavern, simulate 100 steps. How many 12 flashes are there after 100 steps? This one seems pretty straightforward. I think we can do this just by brute forcing again. I mean, there probably is a faster way to do this, but I think we can just brute force this. What I'm going to try, though, is I'm going to try a 3-dimensional integer array, because we need to know whether or not the octopus can flash or not. But they can only flash once per turn, so I'm going to try a 3-dimensional integer array with having a third dimension being whether or not it has flashed this turn. Inputs dot size, and this is, I'm just gonna kind of do it this way. Inputs get 0 dot length and then 2. Oh, I need a name for this. Call it octopi. I don't know if is it actually octopus or octopi. I don't actually know what the plural of it is. But at any rate, let's go then through our strings here. While I is less than input dot size, I plus plus, and then go through each character in inputs get I length J, and then we can dump into here. So we can do I, so it's row, column, and then whether or not it's flash on, so 0 is going to equal, let's just do string. Let's make our life a little bit easier here. Not really easier, but just, simplify it a bit, I guess. And it's going to be char at, right? It's not integer, right? It's, it could be a char. I mean, integer can be a char. We can do char because it'll still be fine to do characters and do it that way. So we can then do character at J, and then we can go ahead and assign 1 to just be 0, meaning it has not flashed. And there we go, we've built this up, handled this a little bit nice. So Now that with that settled, now we need to actually do the steps. So we need to do for int I equals 0. I actually do step while step is less than 100. Step plus plus. I can't type. There we go. So let's go through our steps. Now what you got to do is you got to go through the array and figure out how to make each one flash and cascade. We can actually do something similar to what I did, was it day 10 that we had, or now that I've corrected myself, I believe this is still a breadth first search, but it's also kind of the same as a flood fill. And also an edit to this, I was using a stack, not a queue. I called it a queue for whatever reason, I don't know. It's a stack, but not this day though. That's big there. This day, so we had the basins and whatnot. We did the flood fill. I think it's still a breadth first search. It's the same logic for breadth first search, but it's doing a fill instead. But we can sort of use this logic here, where we can go through all of these like this. We can change this though to octopi.size or octopi.length, I guess, and octopi I dot length. We can change to this, and then at this point here we can have a list of, I'm actually gonna steal this point here again because I should just make this like a common class to have as a point. It comes up a lot. We can have a list of points, and this is going to be the toVisit. And we don't care about visited because in this case we actually do want to visit everywhere it gets touched. So everywhere where the flash occurs, it doesn't matter if we've already visited that. We actually still want to visit it, so we don't have to worry about the visited list here. And we're gonna throw into toVisits, and I'm gonna throw in I and j. So if they've already what happens if they've already flashed? It causes an octopus to have energy level greater than 9. It also flashes. This process continues as long as the octopus has. Oh, only when they flash. Oh, okay. Never mind. They don't get reset to 0. Okay, so we don't need the two-dimensional. We don't need this extra 2. Only if they are above 9. So only if they're at 10 or if they get put above 9. Okay, that makes this a little bit easier. We don't have to worry about keeping track of the other index because they don't get reset to 0. We don't have to keep track of that. Okay, makes more sense. So go ahead and do that, and then we'll do while toVisit. Whoops, I didn't have a thing here. While toVisit dot size is greater than 0. We will continue this thing here. So what we'll go ahead and do is we'll just pull off the first point. toVisit remove 0. Remove it from our stack almost here. Or this is a queue. And then what we'll do is we'll access this, and we will. Oh, this is an integer. I'm dumb. I don't know why I thought this was a char. This is an integer. This time I will actually do it. The last time I just parsed the string version. But this time let me pull up the ASCII table. I forget what 0 starts at. 0 starts at 48. So if you take this char out and subtract 48, that'll convert this char to a number correctly. It should. So that should give us our correct number. We don't have to use the parsent anymore. And now we can just do plus equals 1 in this case. Yeah, for this point, plus equals 1. And then we need to go all the directions around and also add all the directions around to our toVisit. We do need to keep track of the number of flashes. equals 0. Oh my goodness. And in this case, if the energy level at this location is 10, right? Because it's only after 9. Only if they're greater than 9 do they flash, right? Cosmic outputs have an energy level greater than 9. It also flashes, but it can only flash once. So it goes to 10. So if it's at 10, we can increase flashes by 1. Okay, and now we get to the point where we have to go through all of the adjacent positions and do that. What's the easiest? I guess we can just throw the if statements we had here, right? We had these. It's a little bit easier. I won't copy them over. We'll do them by hand again. So if I minus 1 is greater than or equal to 0, go ahead and do 2 visits, add new point. That was weird. I minus 1 j. Yeah. And we're just gonna do a bunch of these. So we can do then I plus 1. Actually, let's just go. That's going up, right? So then the diagonal. I minus 1 is greater than 0, and j plus 1 is less than octopi. I mean, this is technically hard-coded, but it's fine. Okay, and then we can go to just this. Let's go j plus 1. This is just going to be j plus 1, and then we move to lower diagonal, which is going to be I plus 1, which is going to be less than octopi length. Still the plus 1 there. So it's now I plus 1, j plus 1. No more j, now it's just I plus 1. And now it's this, except a minus on that, and this is going to be greater than or equal to 0. J minus 1, I plus 1, and then just this check, and then make sure you need one more. This is fine. We do one more if statement here to wrap up the last diagonal, which is this and this. And there we go. So that should add all our 2 visits correctly. Now we should do all the logic correctly. Oh, these aren't I. Okay, let's do, I messed this up. Int row equals p dot row. Haha, I messed this up. My bad. So everywhere we see I, it's actually row, not I. Because we want to be using the point we've pulled off, not the point of the location that we are currently starting with. That would be bad. I could use a finer place for this, but I've committed. Okay, now we should be good. And just like that, this is also messed up because this should be row, row, column, column. No I's and J's. I's and J's only used for this. Right, okay. This is row, column, good. Okay, so that means then is that this is now done, and then at the very end of this, we should be able to do a lap flashes. What we first need to do is at the end of all this logic, when we are ready to go to the next step, we actually go through this one more time and reset all the ones greater than 9 back to 0. So we have to do a check here if the octopi at row column greater than 9, we then reset it to 0. Shall we see if this works? Out of curiosity. Oh. Oh, wait. I messed this up. Only if it flashes do we do this logic here. If it doesn't flash, we don't bother doing the supplemental whatever, right? There we go. Is this right? This doesn't seem... What the heck? That is not what I copied over. Hey, it was right. Sweet. On to part 2. Seems like the individual flashes aren't bright enough to navigate. However, you might need to have a better option. The flashes seem to be synchronized. An example above, the first time all octopus flash simultaneously is step 195. If you can calculate the exact moments when all octopus will all flash simultaneously, you should be able to navigate through the cavern. Was the first step during which all octopus flash. Oh. So we need to figure out when they're all 9. Or when they all flash. Okay. Oh. I feel like this is gonna happen. It might not be too slow. Okay, so what's... Let's just reset octopi. So this is gonna be part 1. We'll just have it reset. And actually, let's just, copy the whole entire thing from part 1 because it's going to become useful here. So the only thing we're going to do differently for part 2 here is instead of flashes being there, we're going to put flashes into this. Actually, no, we'll leave it out here. We'll set flashes equal to 0 here, and we're going to do a while loop here. While flashes is less than 0 start, right? Is less than octopi dot length times octopi 1 or 0. Do that. Right, it's that, because it's step 1 to start, right? Yeah. And so for this case, we want to output the step. I don't know, this might work, it might not. I don't actually know. 324. Hey! Well, that worked out pretty well then. Okay. Not too shabby. I thought that would be a little more difficult, but turns out, no. Okay. Let me go ahead, clean up the code again, and I will catch you guys back in just a second, and I'll go over how I solved this. Okay, so I might have gone a little overboard on the code cleanup, but I really wanted to break things up to kind of make it easier to explain what each individual part was doing and kind of go about that way. So I really kind of split things up into individual methods because honestly, part 1 and part 2 are basically identical. They just have a slight difference that you can now really see with how I cleaned up the code. At any rate though, the first thing we need to do is go ahead and take our input in and parse it into a integer array here to kind of store the flash state or the energy state of the octopus. So this octopi array, which actually looked up, octopi and octopuses are both correct, I guess. Octopi is apparently older. Either way, I like octopi better, so I called it octopi. Yeah, so we basically parse the inputs in, and we have this octopi two-dimensional integer array, which stores the octopus given its row and column, and stores its energy value. From there, then for part 1, we go through and we have to step over 100 times of this logic and make each octopus flash or increase its energy value. To do that, we for every step we go through, we call this flash octopi method, which all it does is store how many flashes have occurred, and then it goes through every column in every octopus, or every row in every column to go through every octopus. And what it does is we reuse our logic from before, where we have this concept of a visited array. To start with this visited array, we go ahead and add the octopus we are currently at, because this one is always going to flash. And then we have this now while loop that will go through while we have a octopus to go to. We will remove it from the to visited array and then add 1 to its energy score. If its energy score state is equal to 10, then we go ahead and make it flash. If it flashes, as the problem says, it causes all the surrounding octopi to it to also have their score get increased, or energy score get increased by 1. So to do that, we just go through and we add all of the 8 surrounding octopi to the to visit the list, and that'll cause this while loop then to continue running until it gets to a point where an octopus doesn't flash, or what gets to a point where octopus don't flash and therefore don't add any more octopi to the to visit list, and therefore this kind of ends. So that's what we're doing. Again, we're using this from day 9, how we did the breadth first search or flood fill, depending on how you look at it, for this one. So that's kind of using that mechanism from that. But that would allow us to go through all the octopi and then trigger that kind of, that waterfall effect that you could have with the octopus king energy levels and flashing and whatnot. But this also makes sure that we visit all the octopi in the array and add 1 to its score at least. So that's how this flash octopi works, and again, it returns the number of flashes that occur, in which case for part 1 is just adding up into a sum total. We also have this method here to reset the flash octopi, so it just goes through all the octopi. If they have a energy level greater than 9, it resets it back to 0 that way. So that really does it for part 1. Part 2 is basically identical. We parse the inputs into this octopi two-dimensional array, but instead of doing a for loop where we go from 0 to 1, we're doing a while loop, and we're just going while the number of flashes that gets returned from this flash octopi method, while it is less than 100, which, well, this is kind of what this means. The length in it's a 10 by 10 grid, so this is equivalent to 100. This is just a little more generic. While that return value is less than 100, meaning all the octopi have not flashed, we just keep going through this and we keep incrementing our step value until we get to the point where every single octopus, or every single octopus has flashed, therefore making this while statement invalid and false, and then ending that, and then we can just simply output the step value there, and that finishes it off. So again, I went overboard on the code cleanup. This is a lot different than when you just saw from when I finished the coding, but this should be easier to look at and understand, which is kind of why I went with it. But at any rate, there we go. Day 11 is done. Day 12 will be here in less than 12 hours now, so I can see you guys all tonight for that. Peace out. See you later.